have been summarizing all the aspects of quantum computing implementations that we have been dealing with in this course in this week. What we are now trying to do is trying to see how all the different aspects that we have discussed in this course as a part of implementation, how does it work in conjunction to make sure that quantum computing becomes a viability. It is an interdisciplinary field, so it takes a lot of different areas, and therefore, we are spending this last week in a lot of detailed discussion of the different aspects of subjects that we have covered. So, in this lecture, we will be looking into the digital versus quantum computing aspects from the principle of looking at the travelling salesman problem. What we have learnt until now is the digital computing produces serial results. On the other hand, quantum is truly concurrent or parallel. Digital computers need an exponential amount of resources to accomplish a task, which can become polynomial in the quantum sense. That is because quantum computers perform 2 to the power n computations, where n is the number of qubits. So, these are the basic advantages we have taken when we went from digital to quantum. So, some of the very simple examples of the quantum nature has been told in terms of very basics of interference. For example, the 2-slit experiment, where if it is a classical case, then for a single slit the bullets will only come from one of the two places where the holes are. On the other hand, when both of them are simultaneously present, then it produces interference. For example, take a look at a wave. For example, the sound waves, their behavior is something which is very different from when only particles are being considered, classical particles. So, to appreciate this, let me show this once more. So, bullets are classical particles. Let us consider the case where we are going to have 2 slits going on to a detector, but for understanding this, let us start with 1 slit. So, when we have bullets, it passes through 1, here is the distribution. On the other hand, if we have the bullet on the going through the other slit, here is the distribution, only one of them are open. If both of them are open, then what will happen is you will get a total distribution which is of this kind. So, 1, 2, and this one is 1 plus 2. On the other hand, when we do sound waves, let us say, then if we have the similar situation of one slit or the other slit, the initial idea of having one each is fine, but when we have both the slits open, they do not simply show the addition that we just showed you for the bullets. Instead, it shows an oscillating pattern, which is the superposition, which is distinct from the individuals that we talked about. So, that is the wave part or the interference nature of this. So, these same thing extend to the electrons, and just going to show this for completeness. And so, we know that electrons essentially, although they are particles, they behave like wave. But when we are observing electrons, then we do see them as bullets. So, they behave as particles. So, that is the dilemma with quantum mechanics, which is what we are working on. When we go to fundamental particles, which are quantum, then they have both the properties. When we observe them, that is when we make that classical, then they behave exactly like a particle, analogous to the bullets that we talked about, but many of their other phenomena behave like wave like, which is what when we talked about the sound wave. So, that is all the principles of quantum mechanics just summarized here. So, in terms of quantum computation, we have been utilizing the concept of superposition, both 0 and 1, and the qubit representation has been in terms of the number of wave functions that we are using. So, the superposition of states, for instance, would essentially have a concept of amplitude, square of which leads to probability. These are all the concepts that we have taken, and as a result the summation of all the square of the amplitudes for the states would always be equal to 1 in order to make the probability laws to be sustained. So, we have been using these kinds of states, entangled states, superposition states, and we have been representing them either in vector term or in the matrix term. And whenever we want to change them, we talk in terms of unitary transformations, which are essentially unitary matrices whose conjugate transpose is the inverse, essentially ensuring the Hermitian nature of the system is preserved. So, we have shown many a times Hadamard transforms, where we can go from a particular pure state to a mixed state, for instance. We also have talked about other simpler gates, for example, the C0 gate, the NOT gate. C0 is the 2 qubit gate, NOT gate can be a single qubit gate, and so on and so forth. There are visual representations which essentially tell us about the circuits, the wires, the representation of the gates and how they interact. The Hadamard, the C0, and so on and so forth. In order to do something more interesting, we would like to use one of the algorithms which help us in getting forward with the ideas of computation, and one of the major ones, as we have discussed, is the Grover search algorithm, which is in polynomial time, whereas the one in Shor's algorithm is in exponential time. However, the Grover's algorithm has the advantage of wider applicability because it is looking for a search. So, its analogy is always given with respect to searching an unsorted set of data, for example, a phone book to find a specific number without rearranging. So, the idea always have been to magnify the amplitude of the chosen number, and always we use the concept that there is an oracle which knows the solution. So, we flip the amplitudes of the selected items and rotate all the amplitudes around the average, and repeat this until the selected items probability of being read is greater than half, so that it can be observed. So, in terms of graphical representations, this is what we have done earlier, that once we get a marked system, we basically can go through the flip and then average them and then flip all the amplitudes around the average to get the marked state amplified. The time complexity, as I mentioned, it is in terms of square root of n, whereas in terms of a normal classical search, the minimum number on an average that you require is n by 2. So, there is a large enhancement when we go to Grover's algorithm. Now, we would like to actually extend this problem to the travelling salesman problem. That is because the principle of a travelling salesman problem is that they require going through the different paths with different levels, and the difficulty is that it is not possible to go through the search in this particular case in a simple polynomial structure as it is possible for a classical computer. So, here is an example of a travelling salesman problem, where the A, B, C, D, E are the vertices or the points into which the travelling salesman is supposed to go. That individual can take different paths, and that is roughly the basic idea behind this problem to start with, and they can have different weightage factors depending on how many times a particular path is being travelled versus the other. So, here is an example of a path which is been shown here, where this particular path route can be taken to go to all the 5 points that we have discussed. So, this is sort of like a moving target travelling salesman that we just discussed, that the target itself is moving, so that you can do a traveling salesman moving target point of a problem. So, we have this origin from where it starts, and we have the particles or the points move with respect to the origin. So, these two are moving away, whereas the other two are moving closer to the origin, and while this happens, as you can see here, we define this problem as the moving target traveling salesman problem. And depending on how they move, we have these initial and the different positions as we have defined here. So, this is the basic idea behind this moving target traveling salesman problem. So, it is a very difficult problem because it is an intractable problem. It is non-determinate polynomial hard, because the classical traveling salesman problem, which is generally without the moving target, is a NP complete problem, whereas the classical TSP can be reduced to a moving target traveling salesman problem TSP under this regime where it is a NP hard problem. So, by giving some velocity to each of them, we can get this. So, the non-determinate polynomial complete set means that it is contained in the non-determinate polynomial kind of principles, and the decision version is based on the tree path with time which is less than the time that it takes. Non-deterministically travel all the paths. If one exists with time less than our time t, return true, else returns false. So, this is one option. This is contained in, both of them are contained in the non-determinate polynomial version. The other version is the optimization version, which is the what is the minimum time path that is taken, where the upper bound of time with initial random path. Then binary search the range by testing t by 2, t by 4 etcetera to find the optimal minimum time path. So, this is a NP complete problem into which we are trying to see how this search is going to work or not. So, in the classical sense, it is a very difficult problem because whenever this is necessary, it needs to be able to visit each and every element of the path, which means that each of these would take that many time travel paths, and that is why it is a very non-determinate polynomial kind of a complete path that is necessary to be taken classically. In the quantum computing case, however, it is possible to traverse every possible path by using some tricks of quantum computing that will be shown, and then once that is possible, then we can have a search through all the paths superposition to find the shortest route. So, this key element of superposition which exists in the quantum computing way of looking into this problem enables to take advantage of the superposition of the different paths once they are all possible to be traversed. This was a problem which was initially looked at by Rudolph by utilization of superposition of cubic bipartite graph in linear time. In terms of cubic means all the nodes have degree 3, bipartite means the nodes are partitioned into two groups, each node is only adjacent to nodes in other group. So, this is the advantage of making this particular approach where it was possible to come up with a cubic bipartite graph in linear time by utilizing this principle. So, here is an example of this problem. We take the same condition of a bipartite cubic graph in which we will be using the 4 qubits such that they are going to come in a set, so that they can interact with the first part and then can get superimposed into the two different sets. One set is between 1 and 2 and 1 and 3, and the other one would then be put up with the other two sets, and so the superposition grows as we have shown here. Now, the potential problem in these cases is that the extracting the Hamiltonian path, and the second problem would be finding the cycles, but not the path. And the actual fact of this kind of a graph theoretical approach is that only works for cubic graphs. So, in terms of solution to the first problem of extracting the Hamiltonian path, only the paths containing all ones in the first register is the question which we. So, in that case we can use the Grover's algorithm. So, the first part where we are only going to focus on only the ones in the first register, we can utilize the Grover's algorithm. For the second part, we can use the black box for Hamiltonian paths to solve for Hamiltonian cycles, and that corresponds to the graph theoretic approach of Hamiltonian paths. And finally, for non-cubic graphs, we can make all nodes have the same degree, wherein the degree must be a power of 2, and the algorithm when all nodes have degree 2 to the power I. So, in step 1 we can give all nodes same degree of 2x. The graph G has n nodes. We find the nodes with the largest degree d, and we find a value x where the node degree lies in between the two possibilities. So, this is essentially how it looks. We have situation which is of this particular kind in this format, wherein we are making the groups of x nodes of the path which can be then mapped into this set, and we can try to find out how these nodes can be contained within this set. So, we go through the graph G node by node and go through the new nodes set by set, and what we get is a set where we can put them together in this kind of a path and link them by using this particular principle. So, the algorithm which requires this quantum transition for nodes with 2 to the power x degree would be having of this format, where we have the control bit coming. If it is all zeros, then it essentially just does a mixing of the two states, whereas if goes through the other sets, then it will be going through this particular set of operations. So, the first operation when the control bit comes, it is going through a Hadamard. So, that is how the first Hadamard works. The next one essentially takes another Hadamard of the 2, and then we are putting in a control knot on top of that. So, the final one is another set of the control knot, and here we are then going back to this set where we start the other control knot set, and then finally we get to the sets that we are interested. And so, here is the circuit that we get. It goes through that many elements that we are going by, and it is an iterative loop. A, B, C are the nodes adjacent to the input. A is the register keeping track of which nodes have been transversed, and in this way all the nodes are being covered. Once that is done, the minimum is being found by measuring the lengths register M. We create a superposition again. Now, we search for all paths such that it is less than M. On an average, we have to do this log of k times, and k is the number of items in the superposition. So, this is how it looks. We go through the iteration 1, then in the second time we make the flip, and so the point about the average keeps on moving, and then finally we are able to go through this entire step. So, we can do this on an average log of k times, so that we can get the number of items in the superposition. So, what we have understood here is the same principle that we did at the very beginning, where we said that we started off with the idea of particles, and electrons, which are quantum system, have the properties of wave like the sound waves, but when observed they behave like particles like the bullets. That is what we did. So, the algorithm works well for all graphs. It may double the number of nodes, but it takes order n steps. When we search the first register for all ones, and the added nodes do not affect the solution. So, these are the key observations for this operation. Now, this can be extended to the overall travelling salesman problem, where we need another register large enough to hold the longest path, and at each step add edge weight into the register. All the paths of length n and their weights would run an algorithm for Hamiltonian cycles, and we will look for ones in the first register, superposition of all the Hamiltonian cycles, and then the Grover's algorithm on some register finds the minimum. So, now after having seen this how it works on regular TSP, it can be then extended to the moving target TSP. In this moving target TSP, each node has a velocity. We find the minimum weight round trip for each of them. So, we add a time register, track the total time elapsed so far for each of these motions. Each step we calculate the time to reach the next node as the motion occurs, and the unknowns for us are the velocity along this direction, v x, v y, and the time. So, in order to determine the optimal path, need to add time to reach the next node to the total sum, need to find the minimum, which is similar to the TSP problem that we just did before, and we have an added time complexity is which is linear. The added time complexity in this case is linear because of the velocity component. So, in summary, what we have shown in this particular approach of Rudolph is that we have extended the Hamiltonian path algorithm for qubit bipartite graphs for travelling salesman problem and for moving target travelling salesman problem. Paths superposition can be obtained in linear time. The Grover search algorithm works in square root of number of objects in superposition, and there are 2 to the power n different paths. So, the total time is order 2 to the power n over 2, which is still in polynomial time, and therefore, this has a benefit over the way how algorithms can be applied to non-determinate polynomials and their principles. We will also look at another kind of problem in this context, which is related to travelling salesman problem in a slightly different way, but generally at this point this idea, the fact that we can search an appropriate path for the different trajectories which are involved in travelling salesman are very important for making progress in terms of algorithm development as well as application of these algorithm developments to problems which are quite difficult to be taken care in terms of classical computing. So, all the non-determinate polynomial problems have been targeted and attempted through quantum computing by using these kinds of principles. So, maybe if time permits, I would actually do one more of this kind of problem in the next class. Thank you.